of these do you do, Nathan?
We do 12, we do 10 a year.
10 a year, okay.
Take the summer off. Oops, don't do that. Told you I would figure out how many people were coming, and I didn't do that.
No worries.
Looks like we have 33 registrants. Oh, Joel is here. Joel is our sponsor share. So Mark would have talked to him. Welcome everybody to the Seattle Building Enclosure Council October meeting. We'll get started in a little bit as people continue to roll in here. All right, good evening, everybody. We're going to get started with our SeaBEC meeting this evening. My name is Nathan Sini. I am the president of the Seattle Building Enclosure Council, which is a nonprofit that's set up to improve the knowledge of building science throughout the greater Seattle area. We've also recently merged with the Spokane Building Enclosure Council. So we've added those folks to our distribution list, and we'll continue to do virtual meetings so that we can keep those folks connected as well. All of this works through our very dedicated team of board members. Our secretary is Amelia Davis. Our treasurer is Jeff Didion. Our education chair is Amanda Prott. If you have an idea for a future presentation, or if you see a good speaker somewhere else you'd like to recommend, please reach out to Amanda. Cliff Marvin is our membership chair. Hillary Roy does our venues. Joel Thornburg is our sponsorship coordinator. If you're interested in sponsoring a future meeting, please reach out to Joel. Bill Thordarson does our student outreach, including our scholarship. Grace Wong is our communications chair and also led the effort on this research grant. Jeremy DeWitt is in charge of our website. Penny Short is a board administrator. And Phil Martinson is our Spokane representative and formerly the president of that chapter. A couple of announcements. The second annual SeaBEC research grant is a $2,000 grant for furthering research in building science and enclosure. Proposals are due by 10/29. And the result is what you'll see tonight as we help to sponsor Teresa's work, and she's going to present on what she's worked on. Oh, I forgot to change that. A couple other building enclosure events. CSI Puget Sound is having a chapter meeting on November 11th called Help the Up and Coming, and then their holiday party is 12/9. IBEC got pushed back a week, so they're actually having a meeting tonight. And then the AIA Architecture for Health Committee is having their fall conference with a resiliency theme on 11, 4, and 5, if anybody's interested in checking that out. SeaBEC has again partnered with the Architects newspaper and is helping to spread word about their Facades Plus Seattle event, which is happening December 3rd at the Motif Hotel. If you've been to one of those in the past, you know that they're a very well organized and run event, and they cover a lot of ground in the 6 hours or so that you're there. Now I'd like to introduce Mark Cron, who is a local representative with Intera, and he will be bringing on Chikashi Tanaka from the Maxell Corporation.
Thank you very much. Good evening. My name is Mark Crone from Intera USA, and thank you for allowing myself and my colleague, Mr. Chikashi Tanaka from Maxwell, Japan, to sponsor the SeaBEC webinar this evening. Intera USA is an importer-exporter of building materials, and Maxell's MAP system is one of our imported products. The MAP system, Maxell Airtight Products, is a group of products that are designed for exterior wall penetration sealing. Intera USA is located in Renton, and we would like to hear from any of you if you have any additional questions once Mr. Tanaka has given his talk. Thank you very much. And here, may I present Mr. Tanaka from Maxell. Please, Mr. Tanaka.
Thank you, Mark, for your kind introducing. First of all, let me say thank you for this opportunity to sponsor your meeting and to introduce our new product. My name is Chikashi Tanaka from Maxell, Japan. I'm in charge of the marketing department for the US market. Today, I'd like to introduce our MAP system, Maxell Airtight products. I have had many opportunities to talk to people in the building industry, but many people wonder why Maxell is in the building industry. So first, let me briefly introduce our company Maxell. Maxell was founded in 1961 and started out producing batteries. Afterwards, as you may know, we have been manufacturing audio tapes and DVDs for almost half a century. Since 2010, we have diversified our business in response to changing times. Now we are manufacturing not only batteries, which we have been making since our founding, but also deodorizer, project lenses, and various building materials. One group of these products is our map system, which I'm going to talk about today. These are AAMS 71113 approved adhesive tapes and rubber grommet sealing products. Our target for this adhesive-related material is for residential housing and commercial construction. The details will be described later, but the strengths of our products are high durability, excellent waterproofing, and air tightness, seals around exterior wall penetrations. Focusing on the current market trends, building codes and general building practices are looking at sustainable houses as they are becoming more widespread with increasing global awareness of the environment and energy conservation. The function required for sustainable houses are air barrier, water barrier, and moisture control at a high level. So we believe that our products are able to make a great contribution to sustainable housing. I would like to talk about our products that are currently sold in the United States. Currently, we are selling exterior wall penetration, pipe, and wall sealer that seals the gap around the pipe penetration, and air sealing and flushing tape that seals the gap between wall fittings. As mentioned earlier, our products are high-quality tapes and self-adhesive that are easy to use peel and stick grommets that have a high air tightness, waterproofness, and high durability aspect to them. In addition to these functions, another major feature of our product is excellent workability. Today, I will explain details about pipe and wall sealer used around pipe penetration. Products commonly used today around pipe penetration are spray foam, adhesive tape, and tape-on or nail-on grommet. All of these products have problems and are time-consuming work with large variation between workers on how they are installed. Therefore, we have developed high-quality, easy-to-use product for air tightness around pipe penetrations. The products we offer are shown at the bottom of the page, pipe and wall sealer. This is a sheet-type product in which a rubber sheet and butyl adhesive tapes are integrated, and the hole is made in the center for the pipe to pass through. The construction method is very simple. Insert the grommet around the pipe and insert it all the way. Then peel off the release paper and stick it to the wall. It takes less than 30 seconds per pipe. Also, the finish is a perfect airtight seal. The main point I'd like to make in this section is that our product helps keep labor costs down because it is a product that anyone can easily install. In addition, since there's only one way to install it, there is no construction variation between installers, so it is a product that can be used with confidence. Lastly, I'd like to talk about our quality. MAP system, pipe and wall sealer complies with AAMS 71113, which is required for airtight and waterproof tapes and grommets in the United States. Here we show the value of our self-adhesive strength, which is an index showing the ease of sticking to substrates. As shown here, it has a much higher value than the standard used in the United States. In addition, even after accelerated deterioration tests, the value did not decrease. From this result, it can be said that our MAP system self-adhesive pipe and wall grommet sealer and tapes are high quality and will last a long time. Before I finish, I'd like to point out the main points again. Our products are high quality, eco-friendly products, sustainable for sustainable housing, and have excellent workability and will last a long time. If you have any questions, need more details, or would like to get pricing, please contact myself or Mark Cron from Intel USA listed here. That's all my presentation. Thank you for your attention.
Thank you very much, Tanaka-san. It's great
Yeah.
to learn about new products and as the market develops. It's always new things. The presentation this evening is by Teresa Moroseos with the UW Integrated Design Lab, and the topic is parametric tool development for evaluating embodied carbon and operational carbon in schematic design. Teresa is a Master of Architecture and a postdoctoral scholar at the Integrated Design Labs in the Bullitt Center, and has worked in architecture, taught at the undergraduate level, and worked on energy, passive solar, and daylighting simulations. Teresa, welcome, and please take it away.
Oh, thank you. Okay, share my screen. All right. Good evening, and I want to start off by thanking SeaBEC for sponsoring our research project and for also inviting me to come and share progress for our research thus far. So this evening, I'm going to be talking about the research tool that we developed with SeaBEC, the SeaBEC research grant. It's called a parametric tool for evaluating embodied and operational carbon in schematic design. So my outline for the presentation today is I'm going to be introducing the UW Integrated Design Lab, tell you a little bit about myself and the research group that I work at. I'm going to be introducing the parametric tool that we developed at my research group. That was, the intention was for it to be used in a University of Washington architecture research studio. So I'm going to talk about that research studio a little bit. And then I'm going to get into the details of the parametric tool, some of the inputs and outputs that we developed. I'm going to quickly go over some sample student work that came as an outcome from that research project. And then I'm going to be talking about how we're building off of the development of this tool and how we're using it in our research, and then lessons learned. So a little bit about the Integrated Design Lab. We are a research group in the Department of Architecture, which is part of the College of Built Environments. We have 4 senior staff members. 2 of them, Christopher Meek and Heather Burby, are also faculty in the Department of Architecture. Deborah Sigler runs our tour program at the Bullitt Center, and I am a researcher that joined the IDL about 1.5 years ago. Before that, I got my bachelor's in civil engineering at UW, got my master's in architecture, worked a couple of years in a Seattle architecture office, and then came back to academia as a researcher and postdoc. And we also have research staff, usually students from the Department of Architecture work with us. And right now we have Andrew Baltimore and Preston worked on this tool with us. So I definitely want to thank him for all of his contributions. And a little bit about the Integrated Design Lab. So we're in the university. We teach, Chris and Heather teach courses at UW. I participate and help with their teaching. And we also have a strong component of consulting work. We help architects with projects. We act as consultants for daylighting and energy analysis. And then we also perform our own research regarding high performance buildings, assessing high performance buildings. I'm particularly interested in daylighting and energy analysis. So the University of Washington, UW Spring 2021 Research Studio was really what started the idea of building the tool that I'm going to be talking about. And this research studio was taught by Tomas Mendes Echenicosia. He is a professor at UW, Christopher Meek, who is the director of the IDL and also a professor at UW. And then I worked on it, and Preston as well, as I mentioned. And the objective of this studio was to investigate the potential of mass timber buildings to reduce both embodied and operational CO2 emissions with the help of parametric models, building performance simulation, and computational structural design tools. So this studio started in the spring of 2021, but the development for this tool that the students were going to use to assess their building designs for operational and embodied CO2 emissions started in the fall of 2020. And this research studio is part of the graduate research program. And it's the last studio that students take before they graduate the master's program in lieu of a thesis. So we had 3 objectives for the tool. The first one is we wanted this tool to be easy to use. And the first piece of that is we wanted it to be based in software that the students are comfortable with and that they've used before. So it'd be easily adopted and really intuitive to use. So we used Rhino as the basis. Rhino, if you don't know, is a 3D modeling software that a lot of architecture students use. And Rhino has a plugin called Grasshopper, which is a visual programming language. And Grasshopper has predefined scripts. They're called components. And that's what these are, all these rectangles you see here are little scripts that are bundled. And so Grasshopper has native components, but then it has components that you can make yourself using Python. And then it also has components that you can download. So you can download other people's components. And we use some open source components created by, it's called Ladybug Tools, that helps package energy models. And I'll talk about that a little bit later. Another piece of being easy to use is we developed it so that the students would only have to put in the outline of zone geometry and some simple inputs, and then it would run basically an energy model to compute operational carbon, and it would also take area takeoffs to compute embodied carbon. So the second part of the tool was it really needed to assess operational carbon for their designs. So this is supposed to be super quick and easy for the students to use, just outlining zone geometries, put a few inputs, it packages an energy model, it runs it through EnergyPlus, and then it calculates CO2 emissions. And then the third goal, as I've mentioned, is assessing embodied carbon. And for the embodied carbon piece, we focused on the embodied carbon of the structure and the envelope of the design, because this is the primary contributor of embodied carbon of buildings. So we calculate the embodied carbon of the materials and calculate the CO2 emitted from the extraction of the raw materials to create the materials, the structure and the envelope, and the transportation. And I'll go into a little bit more about what measures we use for embodied carbon. So on a big scale, from the operational piece, we wanted to bring in design inputs, simple design inputs. We wanted to run an energy model through EnergyPlus. We wanted to package the results in a way that the students could easily digest and comprehend and disseminate the results. And similarly for the embodied piece, we take those same inputs, so the students don't have to give us any other inputs. It's all packaged in the same input. And then it pulls from a database called the EC3 database. It stands for the Embodied Carbon in Construction Calculator. database, which was developed by the Carbon Leadership Forum at the University of Washington, and it catalogs the embodied carbon of different materials. So we we have the tool and we preset materials. We grab the materials from the EC3 database, and then we calculate a carbon emissions for that design and package the results and disseminate it to the students. So that was the goal for the whole tool. A note about the embodied carbon data that we used this EC3 database, and it uses a cradle to gate methodology to calculate embodied carbon. So that means that it calculates, it shares information for embodied carbon from the raw material supply, the manufacturing, and the production process of the materials. So that's the, we're basically calculating the carbon emissions associated with the production stage of the materials. And we decided to host all of the material for this tool, all of the coding and the Rhino files, the Grasshopper files on GitHub. And this tool is accessible, it's open source, so anyone can go and download it if they're interested. So GitHub, it's basically a repository, it's similar to a Dropbox. And once students downloaded the files on their local machine, they can start to use it. And then as we updated throughout the studio itself, we discovered ways to improve the tool. So we would just push new versions to the students as they were working. And so this is what the actual tool looks like in Grasshopper. It's separated into 3 parts. It has parts for inputs. It has kind of this black box area that the students didn't really have to interact with. It basically grabs all of the information that the students put in. It creates the energy model. It calculates area takeoffs for the embodied carbon calculations. And then there's a results section. So now I'm going to dive into some of the inputs that the students had access to. So the first input that I want to talk about is the location. And the studio was set up to have 3 different studio sites, Seattle, Milwaukee, and San Antonio, in an effort to explore how climate and dirtiness of the grid impacts trade-offs between embodied carbon and operational energy. So we're looking at 3 different climates, type 4, type 6, and type 2. And we're also looking at 3 very different electric grids. So when the tool runs the simulations, it assumes that the buildings are 100% electric. And then we converted the kilowatt hours of electricity used by the building design, and we converted it to grams of CO2 using the carbon intensity of the grid, and each location had a different carbon intensity. And basically carbon intensity is how much carbon the grid emits per kilowatt hours of electricity production. So Wisconsin is the dirtiest. It relies the most on coal. So that one had the most carbon emissions per kilowatt hour. Next was Texas, and Washington's pretty good because we have a lot of hydro. So the grid is cleaner. So those are the 3 sites that we looked at. And the way that the students would choose the site is they go to this part of the tool in the Grasshopper script, and they simply choose a location with the dropdown. So from a user experience, they just choose this dropdown. And then behind the scenes, we had a database of all the weather files, the TMY3 weather files that went to the energy model. We had the carbon intensity of the grid, And then we also had embodied carbon information for materials that was specific to a location. So the embodied carbon represents the manufacturing process that the materials are most likely to come from. So we also have an input in Grasshopper for the massing geometry. And the way the students would input the massing is simply, this is showing the Rhino screen right here. And they simply had to draw lines that delineated their zones that they wanted to study in their building. And they just would come to these Grasshopper containers. They contain Rhino information and set these lines to delineate their zones, and they could set up to 5 zones. So this part was really important to us. We wanted the students to be able to quickly change their design iterations. So having a quick way to input simple massing geometry into Grasshopper was really important. So as soon as they set the geometry, the energy model begins to emerge, and then they have to set some other parameters. But this is showing a view of the energy model that was created by putting in this geometry. So this is an example of a 2-zone geometry, and the tool is very flexible. They could put in up to 5 zones, and it could be pretty much any shape they wanted. One important thing to note is that this methodology that we created only gives embodied carbon and operational carbon information for 1 level. So if the levels were the same, they could just copy the information. If they change, then they would have to recalculate embodied and operational carbon for the design as it moves up and down the building. So from a user experience to input the massing, they just choose the Rhino geometry. And that was really the only thing we used Rhino for. And then behind the scenes, it creates the energy model, and it also creates the area calculations for the facade and the slab. And just to mention again, we used Ladybug tools to package the energy model. Those are those components, the open source components for Grasshopper. It created an Open Studio model that was then ran through EnergyPlus. And it was really important for us to use these tools because they are validated. EnergyPlus is created by the Department of Energy, and they're open source. So that we just wanted it to be as accessible as possible, thinking about how people, maybe architects, could use it in the future. And oh, there's a question, is a zone a room? It could be a room. It could be a room. It could be spaces that maybe have different programs, different heating and cooling requirements, or that are separated. And then I think the most important thing for the studio was that by separating the space, the entire floor plate basically, because we're basically modeling floor plates. Separating the floor plates into zones allowed you to understand what the heating and cooling loads were doing throughout the day, because they would be different based on like orientation, for instance. So it allowed you to kind of fine tune and understand what like facade impacts were having on different areas of the floor plate. Yeah, so we had Yeah, so we had 3 different zone program types, and we allowed the students to put in the 3 program types. The retail, office, and residential. So the intent of the studio project was to create a mixed program building. And the way the students would input the zones is from the zone program is from a drop-down menu. These were honeybee components that come from Ladybug Tools, the open source scripts that we were using. And the beauty of using those is that they pull programmatic loads from the Department of Energy reference buildings. So we didn't have to set things like the amount of people in the space and the schedule and the lighting and the electrical equipment. All of these things were referenced from Department of Energy reference buildings using this honeybee script. So in terms of all of these types of assumptions, the students did not have access to change any of this. Like they didn't have access to change the infiltration rate, for instance, which would have a huge impact on operational energy, how tight the building envelope is. So there definitely were a lot of limitations, but we just wanted to give them a quick way to assess basically building massing, window to wall ratio, and building envelope wall assemblies. That's the thing that the tool really focuses on. So that's how the students would choose the program type. And then we also allowed for inputs on the ceiling and floor condition. Since they are just modeling floor plates, they could tell us or tell the tool if the ceiling was outdoors or adiabatic. Adiabatic meaning that there's no heat transfer between inside the zone and outside. So meaning that it's up against interior space. And then the floor condition could be adiabatic or ground. And then this would change the energy model and change the embodied carbon calculations. And then we have the wall construction options. So we allowed the students to choose from different facade cladding types to assess the embodied and operational pros and cons of that decision. The exterior insulation type and thickness, the interior insulation type, the wall framing, and interior finish. So once again, this would change the wall construction of the energy model, and then it would also pull from a database that we created and calculate embodied carbon calculations. And at the beginning of the studio, the students were limited to these decisions, but as the studio progressed, we did change the tool for some students who really wanted to look at the impacts of specific materials. So we added materials to our database and allowed them to customize it a little bit. And we also allowed the students to change glazing parameters. And those parameters were the frame type, aluminum or wood, and double or triple glazing. The window to wall ratios of each facade, north, south, east, and west. And if the building footprint had more than one facade facing in each direction, that window to wall ratio would be applied to multiple facades. So if you had like an L-shaped building with 2 facades facing south, the south window to wall ratio would be applied to both south facades. You could choose between low or high solar heat gain coefficient and also different shading depths. And all of this went into the embodied carbon energy model and also into the embodied carbon area takeoffs. And this is showing an energy model with a 50% window to wall ratio on the south, and then a 20% window to wall ratio on the west, and different types of shading. So the students were able to increase the shading. We assumed material and an embodied carbon value for the shading as well, so they could understand the impacts of operational and embodied. And lastly, we also allowed the students to calculate the embodied carbon of the structure. And the students had two different ways to input the structure. They could either draw out this structural grid, and we were assuming that this was all mass timber, a CLT building. So they could draw out the columns and the beams in Rhino and a core, and they could bring that geometry into the Grasshopper script. And this was only used for the embodied carbon calculations. Or they could manually tell the script what they wanted their bay spacing to be and what bay they wanted their core to be in, and it would calculate it would create a manual or an automatic structure for them. And this was used for the embodied carbon calculations. And lastly, the students could add context. The context has a huge impact on shading. So it was used only for the operational piece, and it was included in the energy model. So this is showing a building with some buildings around it. So once the students input all of those inputs into Grasshopper, there's a part of the script where there's a toggle, and they just had to click it to true. And then the energy calculation would start running. That was a good sign that everything was working well. And then the energy calculation took about 20 seconds. It's super fast. And then they would start to get some outputs. One of the outputs that we generated were Excel spreadsheets. And with each iteration that they ran, they would have a separate Excel spreadsheet, and it was given a name. It was the date and time that they ran the calculation, so they could keep track. And they could also name the iteration, so they could also understand what iteration they were looking at. And then it had a lot of information. It gave you the inputs, the height, the wall assembly R value, the U value, all of the glazing parameters that the students chose. And then it also had the embodied carbon calculations, the total floor area of the different zones, and then the facade areas of the different zones. And then it gave the EUI, the kilobTUs per square foot per year for the different energy uses. So we had cooling, heating, lighting, equipment, hot water. One thing to note is that we ran ideal air load calculations. So these values don't have a COP associated with them. And then they, from that, we calculated total kilobTUs per year, converted that into kilowatt hours, and then used the carbon intensity of the grid, the relationship between kilowatt hours and CO2 emissions based on how dirty the grid is. We used that to calculate total kilograms of CO2. And then we also told them their embodied CO2. And then this value shows the kilograms of CO2 per year. We also calculated it for 30 years to show, like, over a 30-year life cycle, how the two values compare. And that was what they had in their Excel spreadsheets. And then they also had these Grasshopper Pie Charts that were generated. After each simulation, they could quickly visualize For the embodied carbon piece, how much is the slab contributing? How much is the window, the beams and columns, core, and opaque wall? And then for the operational piece, how much the cooling equipment, heating, hot water, and lighting. This little piece is lighting. It's so small that the label isn't there. How much that was all contributing to the total operational energy and carbon. And then there was a comparison between embodied and operational carbon. And they had a slider and they could put it out to 30 years and to kind of get a sense of the relative impact of both. Other things that the tool allowed them to do was they could generate sun path diagrams to understand shading opportunities, especially in San Antonio. This was something that the students took advantage of. And it basically would show the sun paths throughout the entire year. This is showing on a typical day in June, if you're standing at this facade, looking up where the sun would be coming from. So you could see that the ceiling covers, at least from this vantage point, a lot of the sun. And then this building blocks a little bit of the sun in December. So you're gonna have sun coming in to that vantage point during this time of year. And this was helpful information for some of the students. Other information that was really helpful for the students was looking at hourly results. These are charts that are generated by Honeybee. So after the energy simulation runs, they could look at hourly results. This is the months here, and then going from morning to night. This is showing cooling, but it kind of gives you a sense of the loads throughout the year and throughout the day. And then this is showing lighting. One thing that we did add is a light sensor in the middle of each zone. So what this shows is lighting is on a schedule, but when the light level inside the zone reaches a certain level, the lights turn off. So some of that energy is eroded. And so as the students were working on their designs, iterating through different options, behind the scenes, we collected the students' data using JSON files. They would push the data to us through GitHub. And we were plotting the embodied carbon and operational carbon of their designs. And this shows at the end of the studio for all of the iterations that they submitted at different points of their designs, where they fell in terms of embodied and operational. And right off the bat, you can see Seattle has the lowest operational because it's a mild climate, but also because the grid is relatively clean. And then San Antonio and Milwaukee were more problematic. They had to invest in more embodied carbon to get even worse operational carbon results than Seattle because of the weather being so challenging and then the energy grid being difficult. But this was a helpful way to look at the results. It's called a Pareto front, and it's plotting two different endpoints that we want to optimize. So everything, all the simulations that fall in this corner are the optimized solutions in terms of embodied and operational. Of course, the students were taking other things into account because they were also designing a building. So this is a timeline of the studio. Oh, should have written studio timeline here. But so they had workshops throughout the studio to learn about the tool. And they focused first on operational carbon and then embodied carbon simulations. Then they had a whole week where they looked at Pareto analyses, where they looked at that optimization and studied what solutions were the most optimized. And then they went through their design development of their buildings, using the analysis results to inform their decisions, because that was the intent of the tool. And then they got into, it's not represented here, but here, design development. And then they also had deep dives where they focused on one particular aspect of either operational and embodied carbon that they wanted to focus and develop. And then they worked towards their final review. So I'm just going to show some examples of student work, actually just one project that I think did a really good job of taking advantage of the tool. This is a project by Juan Eduardo Quiroga Castillo and Michael Shoemaker, and their site was in San Antonio, Texas. And one thing that they really focused on at the beginning was they wanted to create this is showing their housing floor plate with a modular design. And one thing that they first focused on was what spans should the modules be, because the tool takes spans into account. It also takes the levels above the level that it's modeling into account to estimate the thickness of like the columns and the beams. So they were looking at spans. They were also playing with shading. So they were investigating how much shade depth is optimal, and how much shade depth would optimize operational and embodied together. And this shows the progression of their design, creating these bays and then shifting them and adding shading by creating those balconies. And that led to a huge reduction in energy, a 10% reduction in EUI, and they determined that through the tool. And they ran through a series of explorations. This is showing embodied carbon versus the number of housing units that they could achieve with different structural grids. And this is also an exploration of different window to wall ratios. So they ran multiple simulations. This is just looking at embodied carbon, looking at the impact of the structural grid and window to wall ratio on embodied carbon and number of units. They also did an in-depth analysis of exterior shading. So they looked at when are the peak cooling days, and then tried to determine what would be the optimal length, kind of as a starting point for the balconies that would shade during the hottest days where you would need the most cooling. And then using that as a starting point, they ran a whole bunch of simulations plotting the embodied versus operational carbon of those all of those design variables that I just listed. And they looked at, I think their optimal result was a 12 by 12 grid with an 80% window to wall ratio with a cantilever. And of course, they were also considering a lot of other variables. They were designing a building. This is a very pixelated image, but so the embodied carbon and operational carbon explorations were used as a guide to help them make decisions, but it wasn't the only thing that they used. They had to think about the site, how the spaces were designed, a whole bunch of things. And I think that was one thing that was sometimes challenging for the students, how to use all of the information that the tool was generating to make decisions. And I think this team did a really good job because they started with some assumptions about their design and used the tool to ask questions, to tweak it and optimize it. So I just wanted to touch briefly on some research we have been doing that has been expanding this tool development for the studio. It's a paper that we're working on, Tomas, Chris and I, and it's called on the trade-offs between embodied and operational carbon in building envelope design, the impacts of local climates, energy grids, and supply chains. And basically we're using the studio tool. We started from it and we developed a parametric model from it where we are altering a whole bunch of variables. We're altering the program, this cities, the facade orientation, window to wall ratio. We have 12 different assemblies for each program. We're also looking at air infiltration rates. This is something that the studio tool didn't have, shading devices and glazing types. And we changed the studio tool to allow us to parametrically add these input variables, and it cycles through iterations. So we can run 10,000 iterations with a click of a button after 2 days, like all the simulations are done, and then we can look at the results. Just to give you an idea of what type of things we're looking at, these are the 12 different assemblies that we looked at. We varied the thickness, the exterior insulation thickness, and then the amount of interior insulation to get different R values to understand the relationship between changing the wall type on operational carbon and embodied carbon. This shows the office zone massing that we're using. We're actually just using a single zone. So all the other surfaces are adiabatic, assuming that it's part of a larger floor plate, but we're just focusing on the energy use of that single zone to run all of our simulations. And this zone is taken from the Department of Energy reference buildings for offices. And this shows the embodied carbon differences for our different wall types and the R values. And then these are some of our results. We have, like I said, we ran 10,000 simulations, and each one of these dots shows, represents one simulation. So this isn't all of them. I search for specific input variables, but we have a database of all these simulations, and what we're working on right now is to publish the paper and also publish all of our results that can be easily accessible in a web tool. So people can toggle, they can choose, for this image, I chose Milwaukee office program, a southern facing facade, window to wall ratios from 0.2 to 0.8, double glazing. This shows all of our wall types. The solar heating coefficient is 0.6, no shading, and then I fixed the infiltration rate. And what this is showing is embodied carbon of all of the simulation results, and then the total global warming potential, meaning the embodied carbon plus the operational carbon after 30 years. And what this shows is window to wall ratio makes a huge impact, as you can see, on the total total emissions. That's these jumps right here in the total global warming potential, meaning total CO2 emitted. But then when you look at individual window to wall ratios, which are labeled by color, you can see that the wall assembly makes not as much of a difference as window to wall ratio, but it does make a difference. And it does decrease as you add embodied carbon up into a point, meaning that there is a point where if you add more insulation, you're not getting the operational savings to offset the increase in embodied carbon. And we thought that was a really interesting result. We're still working on like sifting through all of the data, but we plan to like analyze it and publish it soon. So as ending remarks, some lessons learned. I learned that I always need to triple check my units. Unfortunately, a week into when the students were using the studio tool, I realized that I put the insulation value of the windows in imperial units and not SI units. And luckily we figured that out early on, but I learned to always triple check units. And then another thing that I learned was a methodology for assessing operational embodied carbon. Also the tool is only part of the process, and it seemed to be most effective for students when they had specific questions that the tool could help inform those. And planning the bugs and download issues are always going to be a problem. So I think planning for that was helpful. And next steps for us is adding functionality to the tool, which we already have been doing for other research. Right now, I'm working on a paper where I changed the tool to look at internal heat index during excessive heat events and looking at the envelope implications on that. So learning about the tool and learning about ways to create energy models has definitely helped me in the research that I'm interested in. And then we also want to share the tool with the Seattle architecture community. Like I said, this tool is definitely still in progress, so we would love to hear your feedback. And I also want to end with saying thank you again to SeaBEC for the research grant. And that's all I have.
Teresa, thank you so much for your presentation. That was great. Will the tool be easy to modify for additional locations? Is that kind of labor intensive to add that information in?
It isn't too labor intensive in terms of the energy file for the operational piece. That's really quick. We got our energy files from the EnergyPlus website, and then for the operational piece, all we need is the global warming potential for that location, and we use global warming potential on a state basis. And then it would also be a matter of changing the adding information for the embodied carbon in our database for that particular location. So it isn't too hard. Adding the locations for the we included some additional cities in this paper, and it didn't take too long to add.
Oh, great. If anybody else would like to raise their hand or ask a question, you can do that, and I can allow attendees to chime in. So the tool is kind of constrained by the studio environment because you had specific cities and kind of specific uses. So they're kind of pieces to be added to, to add, a school use or something else like that.
Yeah, it was really constrained, and we spent a lot of time. One of the reasons it was so constrained is we wanted to gather, design the results, the operational embodied results for all of the students. And in order to do that, we kind of had to constrain the inputs to make sure that the outputs were all consistent. Mm-hmm. We did allow the students, like later on, to be able to customize their Grasshopper tools, and we worked independently with them to do that. But yeah, just because we were trying to make it as applicable to everyone, I think it did limit the capabilities of the tool itself.
One of the things that I noted about your chart that plotted the projects by location was that the Seattle projects all seem to have the same embodied energy. Was that just sort of a small sample size and coincidental, or yeah, this one? Whereas Milwaukee went, way up in operational.
Yeah, I think there's a few things going on. I think because of the mild climate, the embodied investment just didn't have to be that much. Like you didn't need as much insulation, or you didn't need like exterior shading as much as some of the other cities needed. So I think the students found that, and when they reported these to us, they probably had already discovered that they could scale back a little bit. But in places like San Antonio and Milwaukee, they needed a bigger investment in embodied carbon because of the climate, I think.
Because you'd sort of expect to see a line going down from right to left, right? Or am I misinterpreting that?
Oh, like you would expect to see something like this.
Yeah.
Yeah, that's a really good point. I think what this is showing, and I haven't like, I think our other results are showing this too. Like these results are showing it too, that the impact of the relative impact of embodied carbon seems to not be making as much of a different impact on operational. But one thing, like if we zoomed in here, we might be seeing a little bit of a trend. It doesn't really seem like it though. I think that's a really good point. I need to look into that more. Yeah.
I assume it wasn't a large sample, right? I mean,
yeah, it's not a large sample. That's a good point. And we don't know, I guess, what this data is kind of hard to interpret because one thing that's not staying consistent is like the massing. So it's kind of hard, honestly, to compare like all of the studio projects together because there's so many variables that are changing. Like if we just looked at one particular groups, like we might be seeing that trend where as you increase embodied operational decreases, but yeah, I think that's a really good point. I think that's something that we should like dive into.
all right. Well, apparently no one else has any questions. It's usually a livelier bunch. But we really appreciate your time and the effort that you've put into this tool and just engaging with the SeaBEC research grant process. I hope nothing was too onerous about that, because it's also our first time. So we're learning as we go. Since we have some time left in the hour, I'm gonna kind of give it back to the group and just convert everybody to panelists, because we're kind of missing that networking interaction that these meetings used to have. But you're free to go if you'd like. And yeah, hopefully people can stay and chat for a bit and catch up with folks they haven't seen in a while.
Okay. I'll stick around.
I know Cliff has something to say. Teresa, where did you work in Seattle?
I worked at Weinstein AU.
I don't think I know that one.
It's a mid-level firm in Belltown. And I worked on a couple of fire stations. They do a lot of like civic buildings like fire stations, and they've done libraries, but also multifamily.
Oh, cool.
Okay, now we can start the, why is
There's
it
stuff.
so dark here?
Yeah.
Gosh, my lights out. So good work, Teresa. I think, I wish I understood it all, but you know, it's a little bit over my head. I don't do these sort of energy analyses. I'm not engaged in doing that sort of work. I think Nathan is probably more qualified to ask questions. I'm all about materials. I'm like a materials scientist. So I write specifications. So and now I write specifications for SpecLink. So I'm writing master guide specifications for the software. Are you familiar with SpecLink? Do you know what that is? It's a software that architects use to write specs, like Master Spec is another spec writing software. What do you know about specs? Let me ask you that.
I did not write specs. I looked at specs, but I didn't really spend a lot of time.
So you've seen them.
Yeah, I've seen them.
Is
Yeah.
there a section for embodied carbon in material specification? I mean, that seems like if you're doing a LEED project or a net zero project, that was something that would be important in the specification process to verify.
Yeah, I'm not aware of that. I don't know.
You know, there's a
Have you seen that?
There's a trend these days in, I mean, in fact, Nathan works for an envelope consultant. You know, they're a company, Nathan works for a company that advises architects on the design of their building envelope. And the idea is, you know, design an envelope that, of course, is going to be energy efficient and comply with all the building code, and maybe go a little bit beyond that, you know, you know, this is something that has grown over the last 20 years. I've seen it grown over the last 20 years. All the time that I've been writing specs, it pretty much coincides with the growth of these companies. I remember in New York City, where I come from, there were only a couple at one time. Israel Berger had a firm, and he was an envelope consultant in New York. And then Thornton Tomasetti got on the bandwagon, and then there was always Heinz's, was a good firm, good envelope firm. Simpson, Hager and Gumpertz is a newer firm that does that sort of work back east. And they have offices out here too, I think. You know, I think.
Murad says that there's an LCA language in EDP's requirement that you can insert into the specs. I don't know what any of those acronyms mean. But...
Life cycle analysis.
Oh, okay.
And what's EDP? Off the top of my head, I'm forgetting. But essentially, we add them into our spec and we ask for the information. So if we're getting a product, we ask for if they have a life cycle analysis that they provide it, if they have carbon information for their products, that they give it to us. And so we can kind of build our own library with whatever actually we use. Because you specify a product, but you might specify 3 products. So you don't know what the actual carbon of the product is until you actually choose components or the contractor helps you choose components.
I wanted to ask you, it wasn't 100% clear to me, but in all of the samples that you took, that was always mass timber, that was the structure? Or did you experiment with other materials at all?
We held that constant.
Okay.
So yeah, all of the structures.
And that was just like part of one of the limitations to control the amount of data coming in, right?
Yeah, pretty much.
But it has the capability, and the tool has the capability of analyzing other envelope materials, correct?
Yeah. Yeah, and the wall construction, could be altered, but the structure itself, it was limited to mass timber.
You could change both your cladding and your insulation, continuous insulation, cavity insulation, and all that stuff. Yeah.
Yeah, and the framing type too.
Was it, so you're basically doing floor plate by floor plate.
Mhm.
Is there a way, is it just sort of another step to do an entire building?
Yeah, doing an entire building is actually not too bad, especially like at the early conceptual level. Our tool doesn't do that, but I've since, now that I've learned so much about developing energy models with Grasshopper, I've since created like more sophisticated ones, and there's definitely the option to do that.
Cool.
Yeah, and I think just to keep it user friendly and consistent between groups, I think that's why we chose to do it level by level. But I think in the future, it might be beneficial to think of it differently. Yeah.
Excellent. Can you talk about a little bit more about the cradle to grave versus cradle to gate?
Yeah. So, oh, there was just a question, how does your software interface with EC3? So our software doesn't really interface with EC3. We built a database, basically an Excel spreadsheet for all the materials that we had in our tool. We built it from the EC3 database, but Preston had to manually go and find the embodied carbon of the materials and put it into our database. So it definitely isn't like streamlined, and it isn't directly pulling from EC3. Preston was basically the interface, but
That's why you have undergraduates.
pardon?
That's why you have undergraduates.
Yeah.
Yeah.
So the cradle. So this is something I'm still learning about. In the development of this tool, I was focused on the operational piece, and Tomas, the professor, one of the studio professors, was kind of in charge of doing all the embodied carbon work, and he's thought a lot more about this than I have. But I think this summarizes the cradle to gate and cradle to grave calculations pretty well. So cradle to gate is only the production stage. It doesn't take into account transportation, construction, like actually assembling the materials, and then the end of use. And the reason we chose cradle to gate and the EC3 database is just because of the like breadth of information that's in that database.
Sure.
Like I think the cradle to grave information, from my understanding, I might be wrong, but just doesn't have as much information as like the EC3 tool, which focuses on cradle to gate.
Yeah, it's a whole nother level of complexity. If you've got
Yeah, there's a lot of complexity.
Yeah. Cool.
Yeah, I was just pulling up, this is the web tool that I was talking about, that Tomas is building this, but it contains all of our data for the simulations we ran for that paper I was talking about.
10,000 simulations.
Yeah, so right now you can filter by like all of these different parameters, and then you can plot Pareto charts of different variables. So yeah, you can look at heating EUI versus embodied carbon, for instance. This is looking at Seattle. So yeah, it's cool. And we're gonna make this public. We're gonna publish the link for it in the paper. So yeah, I can send you a link to the paper once it's published.
That'd be great.
Yeah.
Thank you.
How else are you kind of spreading this knowledge?
We are engaged with architecture firms in Seattle, and we've been like sharing the information we learned and the tool with them. There's a advisory board. There's 13 architectural offices that are part of the IDL advisory board, and we presented the studio tool development to them, and so that's one way that we've been sharing the information. And then other than that, this paper that we're writing and the tool itself is open source, so as more people learn about it, like it'll just grow if there's interest.
Cool. Moran had a couple of other questions. Do you include EDPs in the database? So the environmental product declarations?
No. The database is it basically has for each material, the energy properties that we need for the energy model. And then it has the carbon emissions associated with it from the EC3 database. That's all it has.
And then he also asked, have you looked into any structural materials such as concrete or steel for their impact? And I guess that's kind of outside of the.
Yeah, I think that's something that we should definitely look at, but we haven't gotten there yet.
All right.
I hope everybody doesn't move to Seattle.
Yeah. Yeah.
It's too easy to build good here.
You make,
Yeah,
I was gonna say, you
too
make it
easy.
look so easy.
I know. That's one other reason to move here. At least it rains. We have that going
Yeah.
for
I've been
us.
here 4 years now, and I've discovered that this is the best kept secret in the United States, this state.
Yeah.
I love it here. It's wonderful.
Yeah.
Nice.
Wish I moved here a long time ago.
All right. Well, I'm going to let everybody go. Thanks so much for your time again, Teresa, and for everybody participating. It's great to see some faces, and we will
See you guys.
talk to you again soon.
Okay. See ya.
Bye. Thanks again.
Thanks. Bye.